Alright, now we can start solving for problems involving normal probabilities. So for some problems where we have to look for probabilities involving normal random variables, the first step is to formulate that in terms of x, in terms of the random variable that is normally distributed. The next step is to convert that value of x to z and to restate the problem in terms of a z-score. And then once we have converted x to z, then we can find the probability using either the standard normal table or the statistics functions in calculators. Now, for most problems, it would be helpful if we try to visualize it first through a normal distribution to guide us in determining what specific area we need to search for. So our first example is the starting salary problem. In this problem, the average starting salary for this year's graduates at a large university is $30,000 with a standard deviation of $8,000. Furthermore, it is known that the starting salaries are normally distributed. So again, what we know in this problem is that x is the normal random variable, which refers to the starting salary. And this is normally distributed with a mean equal to $30,000 and a standard deviation which is equal to 8,000. So for the first problem, we need to look for the probability that a randomly selected graduate will have a starting salary of at least $30,400. So like what was stated in the earlier slide, we have to formulate this first in terms of x. So we need to look for the probability that the starting salary, which is x, is at least 30,400. So that's how we denote this problem in terms of x. Now the next step is to convert this to z so that we can use the standard normal distribution to derive the probabilities. So to convert x to z, we use the simple formula z is equal to x minus mu over sigma. So in this case, just convert 30,400 to z by subtracting from 30,400 the mean, which is 30,000, and then divide that by the standard deviation of 8,000. So when we solve for this using your calculators, that's 30,400 minus 30,000 divided by 8,000, we will get a z-score of 0.05. And once you reach this point, it should now be possible for us to get the probability using either the standard normal table or the statistics functions in calculators. So again, as suggested, it helps to try to visualize this in terms of the standard normal curve. So earlier, again, it was said that the distribution refers to the starting salary with a center which is at 30,000. And we need to get the probability that the starting salary is at least 30,400. So it must be somewhere here to its right. And what we need is the area to its right. This one. So this is what we are looking for. Now, if we use the standard normal table, we can look for 0.05 in the standard normal table. But remember, the table that we are using gives areas to the left. So what our table will give is this area instead. So if you search for that in the table, what we will get is 0.5199. And since the total area under the standard normal curve is just 1 or 100%, just subtract 0.5199 from 1 and we will get the corresponding probability that we need, which is 48.01%. So the probability that we are solving for is 48.01%. So that's one approach. Now, another approach is to use your calculators. So again, in the calculator, we actually have a function that can compute for the area to the right of any given z-score. So if you just use the R function and then type in the z-score 0.05, the calculator will actually give us a more precise probability, which is 0.48006, or when rounded to 4 decimal places, that's the same as what we would get if we use the standard normal table. So the probability that a randomly selected graduate will have a starting salary of at least $30,400 is 48.01%. Now for the second problem, individuals with starting salaries of less than $15,600 receive a low income tax break. What percentage of the graduates will receive the tax break? So again, it helps to try to visualize the problem first in terms of the standard normal curve. So let's say this is the normal curve, where again the center is 30,000. The problem states that those with starting salaries of less than 15,600 receive a low income tax break. Now we can try to locate 50,600 first in this normal curve, and we know that since the center is 30,000, 50,600 must be somewhere to its left. So let's say this part here represents 15,600. So those whose salaries are less than this, that's this area. Now the problem is asking for the percentage. What is this percentage? The total percentage of those whose starting salaries are less than 15,600. So in other words, the problem is asking for the probability that the salary, or X, is less than 15,600. So the next step again is to convert this to Z. So we use the same formula. That's 15,600 minus the same mean of 30,000 over the same standard deviation of 8,000. So when we solve for this using our calculators, that's 15,600 minus 30,000 over 8,000, we will get a z-score which is negative 1.80 or negative 1.8. So again, once you reach this part, you now have two options. Again, you can use the standard normal table, and since we just need to get the area to the left of negative 1.8, we can just look for negative 1.8 in the table. And if we do that, what the table will give us is 0.0359 or 3.59%. Another approach is to use the P function in the calculator. So that's P of negative 1.8. Again, it will give us a more precise probability, which is 0.03593, which when rounded off to 4 decimal places is also equal to 0.0359. So this is the probability that a randomly selected graduate will receive a tax break. And this is also the same percentage of the graduates who will receive the tax break. Now let's move to the next problem involving exam scores. So in this example, the scores of students in a 100-point exam are normally distributed with a mean of 64 and a standard deviation of 9. So in this problem, the normal random variable x refers to the scores. where the average of all scores is 64 and the standard deviation of all the scores is 9. So for the first question, we need to look for the probability that a randomly selected student got a passing score, or at least 60. So in this question, again, we first formulate this in terms of x. So what the first question is asking for is the p, or the probability that x is at least 60. So the next step is to convert this to z. So that's 60 minus the mean of 64 over the standard dev of 9. And then we solve for this z-score. That's 60 minus 64 over 9. Our calculator will give us a z-score of negative 0.4444 and so on. Now, to standardize our computations, we will always round off our z-scores to 2 decimal places, since the standard normal table is precise up to 2 decimal places. So this is negative 0.44. So again, I will no longer draw the normal curve, but based on this equation, we need to get the area to the right of negative 0.44. So again, we have two options. You can try to look first for the area of negative 0.44 in the table, and then subtract that from 1. So if you search for that in the table, you will get 0.33. That's the area to the left of negative 0.44. And then just subtract that from 1, and you will get 67%. Another approach is to get the probability, or the area to the right of negative 0.44 using the R function in the calculator. So using R and then inputting negative 0.44 as the z-score, you will also get the same probability, which is 0.67003. So the probability that a randomly selected student will get a passing score, or got a passing score of at least 60 is 67%. Now for the second problem, we need to get the percentage of students who got a letter grade of B, or a score between 83 to 88. So to do this, again, we formulate this in terms of x. So basically, the problem is asking for the probability that the score is between 83 and 88. So we have x greater than or equal to 83 but less than or equal to 88. So here we will just convert two values of x to z simultaneously. So that's 83 minus 64 over 9, and 88 minus 64 over 9 as well. So when we solve for this using our calculators, the z-score of 83 is 2.11, whereas the z-score of 88 is 2.67. So again, using the standard normal table, you can first try to look for the area to the left of 2.67 and subtract the area to the left of 2.11, so that we will get their area in between. So in the standard normal table, the area to the left of 2.67 is 0.9962, while the area to the left of 2.11 is 0.9826. Therefore, when we get the difference between the two, you will get the probability, which is 1.36%. Now, again, aside from this, we can also use the stat function in the calculator. So essentially, we will do the same thing. First, get the area to the left of 2.67. So use the p function to get the area to the left of 2.67, and then subtract that with the probability using the p function again for the next z-score, which is 2.11. So in the calculator, it would look like p of 2.67 minus p of 2.11, and the calculator will give again a more precise value, which is 0.01364, which when rounded off to 4 decimal places is also 1.36%. So the probability that a randomly selected student got a score between 83 to 88 is 1.36%. And this is also the percentage of all the students who got a letter grade of B. Now, in the third question, we need to look for the minimum score of the top 5% of all students. So it's quite different now compared to the previous problems. Now it's asking for a score. It's looking for a value of x. So again, it helps if we visualize this first using a normal curve. So we are looking for the score of the top 5%. So we know that the value here at the center is 64. That's the mean. And we know that we are looking for the top 5%, and it must be somewhere here. Right? Let's say this area is 0.05. What we need to know is the value of x at this point. What is that value of x so that its area to its right is 5%. Now, we are given the probability 5%. So using the standard normal distribution, let's say when we convert this to z, we know that the value of z here at the center is 0, and we will need to look for the corresponding z-score of this value of x. And there is a way to write this properly. That's the z-score whose area to its right is 0.05. So that's z with a subscript of 0.05. Because this area is also equal to 0.05. Now again, we can easily find this in the standard normal table. So again, there are two ways to do this. You can either look for 0.95, the complement inside the table, or just look for 0.05, but make sure to convert the z-score to positive, because what we're looking for is a positive z-score. So if we search for 0.95 in the table, there is no probability that is exactly equal to 0.95. Instead, what we have are 0.9495 and 0.9505. So again, our rule when this happens is to get the average of the corresponding z-scores of the two closest to the one we are looking for. So the z-scores are 1.64 and 1.65. So the average of the two is 1.645. So this z-score must be 1.645. But again, the problem is not asking for a z-score, but it's asking for the value of x. It's asking for a score. So we know that the z-score is 1.645. So we will just work backwards in order to solve for the corresponding value of x. We know that the average is 64 and the standard dev is 9. So using simple algebra, we should be able to get the value of x So when we solve for this using calculators, we will get 78.805. So the minimum score for a student to be part of the top 5% is 78.805. Now for the fourth question, we were told that if a total of 61 students got an A, or a score of at least 92. Now again, it's asking for slightly different information, which is the total number of students who took the exam. So again, if we try to visualize this, according to the problem, 61 students got an A. So let's say, again, this is the standard normal distribution of the scores. The center is 64. The students who got an A got scores of at least 92, and 92 must be somewhere to the right of the mean, which is 64. So let's say this is 92. This area here represents the students who got an A, and according to the problem, that's a total of 61 students. Now, unlike the previous problems, we were not given that area. We just know that 61 students in total got an A. Now, what we have so far are different values of X. We have 64, that's the mean, and we have 92. So the next value that we can get here is the z-score of 92, right? So again, we can convert this to the z distribution, and here the center is 0, but for 92, the z-score, again, that's calculated using the same formula, which is x minus mu over sigma, or 92 minus 64 over 9, that's 3.11. So the z-score here at this point is 3.11, and now that we have the z-score, we can now determine this area, right? That area is basically the probability that z is at least 3.11. So here I'll go straight to the R function in the calculator, and the probability to the right of 3.11 is a very small probability, which is 0.0009 93551. So that's according to the calculator. Now if we use the standard normal table, again, we can look for 3.11 in the table, and then the table will give you the area to the left, so subtract that from 1. Or again, you can use symmetries. Instead of looking for 3.11, you can just search for negative 3.11 in the table, and the table gives us a value, or the probability, that is up to 5 decimal places only, which is 0.00094. So 61 students, that's 0.00094 of the total number of students who took the exam. So if the total number of students who took the exam is n, and we multiply that to 0.00094, that should be equal to 61. And using simple algebra, we estimate that the total number of students must be 61 over 0.00094, or approximately 64,893.62 but again, this is n, that's total number of students, so it has to be an integer. We will round this off to 64,894. So there were a total of 64,894 students. Now we will move to the body mass index problem. So in this problem, a body mass index or BMI of more than 25 is considered overweight, while a BMI of less than 18.5 is considered underweight. Those in between are considered normal. If a public school's records showed that 2.74% of the students were overweight and 29.81% were underweight, determine the mean and the standard deviation for the BMIs of the students of the said school. Assume that the BMIs are normally distributed. So again, in this problem, X refers to the BMI, and we don't know the mean and the standard dev, and that's basically what the problem is asking for. We need to solve for the mean and the standard dev. Now what the problem has given us so far is that when we try to visualize that in a normal distribution, two 2.74% of the students were overweight. So overweight, again, according to the problem, a student is considered overweight if the BMI is more than 25. So if X is greater than 25. So 25 must be somewhere here to the right of the center. Let's say this is a BMI of 25, and this shaded area here, according to the problem, is 2.74% or 0.0274. On the other hand, the percentage of students who were underweight is 29.81%. And for a student to have a BMI of underweight, the BMI should be less than 18.5. So basically it means that the probability that X is less than 18.5 is 29.81%. So let's say this is 18.5. This area, according to the problem, that's 29.81%. So this is the information given to us so far. So our next step is to find a way to solve for the mean and the standard dev using this information. Now, we are given probabilities, we are given values of X, so we can try to write these values in terms of Z. So we know that when converted to Z, this value 18.5 must be equivalent to negative Z sub 0.2981, right? The corresponding Z-score of 18.5 has an area of 29.81% to its left. That's why it's denoted as negative Z sub 0.2981. Meanwhile, the corresponding Z-score of X equal to 25 can be written as positive Z with a subscript of 0.0274, because the Z-score has an area of 2.74% to its right. Now, based on this, we can try to derive the value of the mean and the standard dev by writing 18.5 in terms of Z. So again, we don't know the value of Z. That's negative Z sub 0.2981. and that's the value of x, 18.5, minus the mean over the standard def. And that's the same case with the other side. So that's z sub 0.0274 equal to 25 minus the mean over sigma. Now, we can actually find the z-scores since we have written them in this way. We can use the standard normal table to get the z-score with an area of 29.81% to its left. And we do that by searching for 0.2981 in the table. So if we look for 0.2981 among the different values inside the standard normal table, we can actually find that exact probability of 0.2981, which is at the intersection of negative 0.5 and 0.03, which means that this z-score is actually negative 0.53, and that's equal to 18.5 minus mu over sigma. Similarly, we can also look for the corresponding z-score of 0.0274. So you can either look for the complement of 0.0274 in the standard normal table, or directly look for 0.0274 in the table, but just make sure to convert the z-score to a positive z-score later. So if I search for 0.0274 in the table, I'll find that exact probability, and that is at the intersection of negative 1.92. So a z-score of negative 1.92 has an area of 2.74 to its left. So the z-score with the same probability to its right must be positive 1.92. So that's 1.92 equal to 25 minus the mean over the standard def. So we now have two equations with two missing values. Therefore, from algebra, we can use systems of equations to solve for this value. So we can simplify the first equation as mu minus 0.53 times sigma equal to 18.5, right? Cross multiply and then transpose mu to the other side. Now for the second equation, that's mu plus 1.92 times sigma equal to 25. Now, at this point, I leave it up to you to solve for the values of mu and sigma using systems of equations. In order for me to arrive at the final answers, I'll use the equations mode in the calculator. So I'll input the values. Positive 1, that's a constant for the first missing variable. The constant for the second missing variable is negative 0.53. And the value at the right hand side is 18.5. For the second equation, constant is also 1. Constant for the second variable is 1.92, and the value at the right hand side is 25. So the calculator automatically solves for the mean, or the value of the first constant, and that's 19.9061, and the standard deviation of 2.6531. So that's how we approach this problem. So again, it's quite different from the other problems, but again, since we started with the diagram, it was easy for us to identify the values that we can obtain next, and then eventually it led us to two equations that allowed us to solve for the mean and the standard def.